Delayed, that's fascinating. Live streaming is delayed. Right, I think we're all good. Delayed, that's fascinating. Live streaming is delayed. Off. And
So I should unmute. Is this better now?
Can you hear now? Yes.
And should I also turn on a video? I guess I should, right? Because I'm using. Okay. All right, good. Yeah, sorry about that. So this is Lili Dunn, a student of Kevin Ingersoll, and then we've also collaborated with Stefan Kirchner. A lot of the work that I talked about on Monday and what I'm going to describe today has been strongly influenced by the ongoing collaboration with Silke Paschen and her group from Vienna. And I, in particular, on the superconductivity topic, I've had extensive discussions with Frank Staglish, Joe Thompson, and Gilbert Olonisen, and others from this area. So here's the outline: quantum critical metals and the loss of quasiparticle of the quasiparticles. This is mostly covered in talk 1 on Monday, and there's one particular topic that I ran out of time, and it might as well be covered today because directly connects with the main topic that I want to address in this talk, which is the superconductivity out of the quantum critical metals, and is primarily described in this paper. So perhaps one way to summarize the question that that's behind this, motivates this work is, can a quantum critical metal that lacks quasiparticles lead to high TC superconductivity? And if it can, how does it happen? Now, I have to define high TC superconductivity because I'm talking about heavy fermion superconductors whose typical TC is 1 or 2 Kelvin. Although the F electron systems TC has reached all the way to 17 Kelvin or so in the F electron based systems. But there are plots like this which have been around, and this one is courtesy of Joe Thompson, which says that if you look at primarily the cerium based F electron superconductors, TC divided by suitably defined effective Fermi energy scale is on the scale of a few %. And you can look at the TC of the cuprates and suitably defined temperature scale. That's roughly also a few %. And these 5F based highest actual TC superconductors in the F electron-based systems roughly also have the same ratio of TC to the characteristic scale. And so in fact, these lines are linear lines and spanning scales about 3 decades. And now scale plots like this could at most be suggestive. So perhaps shouldn't be taken too seriously, but it motivates the question. Can we, if we define high TC as TC reaching a few % of the Fermi energy scale, effective Fermi energy scale, as opposed to in BCS where it's 10 to minus 4 or so, is a mechanism to address that. Now, superconductivity in F electron-based systems has been studied based on spin fluctuations and other ways, but the interplay between quantum criticality and superconductivity on the one hand, and also the kind of quantum criticality for which I described on Monday, how that influences superconductivity to a large extent has not been addressed. And this is a very rich set of superconductors. The total number of F electron-based superconductors has reached about 50. And if you enumerate through these numbers, the majority of them seem to be at least could be connected to some either identified or putative quantum critical points, and with antiferromagnetic correlations that have been, again, either be identified or suspected. So we are going to, so that motivates the work that I'm going to present. Quantum critical point by now is familiar. I just want to mention again what I described in a bit more detail on Monday, that if you look at, I can look to the back end of envelope calculations to see that entropy is enhanced. If you do isothermal scale at the small but non-zero temperatures, entropy will be maximized near the quantum critical point, and so that's therefore it's prone. It's a system that's prone to developing unusual excitations and emergent phases. The questions, just to show a few slides of what I talked about on Monday. One could, in the antiferromagnetic metallic quantum critical points, the Landau framework was formulated by Hertz and worked on by subsequently by many others, Andy Millis and others. And it has the fluctuations of the order parameter that couple to well-defined electrons, and because the majority of the Fermi surface would not be coupled with the non-zero antiferromagnetic wave vector to another point on the Fermi surface, the quasiparticles remain intact, and the kind of phenomenology and general questions motivated the addressing the issue of whether there could be critical modes that go beyond the order parameter fluctuations. And so I'm going to, from this point on, narrow it down to heavy fermions, which emphasize not only the bare conduction electron degrees freedoms, but local objects such as the local moments. And the starting point for today's talk is what I talked about on Monday, namely, we can have the type of quantum critical points that not only feature the fluctuations of the antiferromagnetic order parameter, but also the critical destruction of the Kondo singlet that's marked by this E star local that is in a sense an infrared way of defining the Kondo scale. There's an ultraviolet way of defining the Kondo scale, and interchangeably for the rest of talk, I'm going to call it T naught, as I already did, or TK0, and effectively for these F-electron-based systems, it serves as the ultraviolet definition of the Fermi scale. So that's where the cutoff is, and scaling, etc., happens at low energies, low temperatures, below this scale. I also described on Monday the physics, electronic physics associated with the destruction of the Kondo effect. Namely, you have these composite fermions that are supported in the excitation spectrum by the Kondo singlet ground state, and that expands the Fermi surface to be large, while if the Kondo effect is destroyed, the Fermi surface is formed by the conduction electrons alone. So, this is the summary of my talk on Monday, and I ran out of time and didn't get to this charge response with dynamical scaling, which actually connects to the question of the picture for superconductivity. So I want to quickly run through this part. So the question in many ways, at least for us, was motivated by the observation of a singular charge response at a quantum critical point that involves antiferromagnetic to paramagnetic ground states. And this is the h bar omega over kBt scaling of the optical conductivity in the unusual frequency range that Eugene Demler was talking about yesterday. in the energy range that's of interest is around terahertz. So this was the effort made by the Vienna group. We were making these thin films of the ytterbium rhodium to silicon-2, and my colleague John Kono, his group did particular student Xinwei Li did the terahertz optical conductivity measurements, and lo and behold, the h bar omega over kBt scaling was observed. The measurement has not gone substantially below h bar omega over kBt less than 1. So in that sense, there's still analysis experiments to be done, but it's already encouraging to ask question, could an antiferromagnetic metallic quantum critical point, could the charge sector become singular? So we look at this problem both at the effective model, both Fermi-Kondo model and in the lattice in the CeCu₂ problem, and showed that there's an object which carries charge degrees freedom and whose correlation functions indeed satisfy omega over t scaling as shown in this real frequency domain calculation, and also in this imaginary time quantum Monte Carlo calculation in this EDMFT approach to the Kondo lattice. And these drops here are similar to what I talked about on Monday on real frequency. Once frequent energy reaches above this fractions of T naught, kBt naught scale, it goes outside of the scaling regime. And there's other works that has addressed related aspects of this problem. So quantitatively, the quantum critical point that involves the destruction of the Kondo singlet has this additional critical degrees freedom associated with the destruction of the Kondo effect. So that makes the electronic degrees freedom that's also critical, and that's in fact behind the quantum critical point being described by an interacting fixed point as opposed to be a Gaussian fixed point that one would get in the SDW formulation of the quantum critical point. And so this interacting nature of it is, as I also said on Monday, is responsible for kBt being the only scale in the problem, and that leads to the h bar omega over kBt scaling that I discussed extensively for the spin responses on Monday, but it also would influence the charge responses because the electronic degrees freedoms are also critical. And this captures the feature that even though the Kondo singlet amplitude is non-zero on the paramagnetic side and approaches zero as the quantum critical point is approached, the involvement of the charge degrees freedom can be formulated as a dynamical Kondo effect that the Hamiltonian still contains antiferromagnetic Kondo coupling. So whatever that's happening in the spin sector is also coupled to the charge sector, and so much so that the charge degrees freedom are also turned critical. While if it's a Landau type of quantum critical point, you would expect singular responses only in the order parameter dynamics, and in this case would be in the spin channel. So for the purpose of this talk, the important point is that what's happening in the spin sector will influence the charge sector, and so that raises the question: can this kind of criticality with quantum fluctuations that have a huge spectral weight, could that influence, for example, superconductivity, which involves the charge sector. So this was written for the Monday talk. But so that's where the connection between the quantum critical points that have lost quasiparticles with the question of superconductivity. Through this consideration of charge channel singularity and dynamical scaling, the link we believe is this is a bridge to go from the critical singularities to the question about superconductivity. And I just want to finish this part by showing a calculation that we recently did in the particle hole asymmetric regime of the post-Fermi-Anderson model, meaning the mixed valence regime. Physically, we were actually motivated by some of the very interesting recent experiments done on these cerium 111 systems, which are mixed valent. The Kondo, the ultraviolet Kondo scale is on the order of 200 Kelvin or so, but there's still very interesting charge. The mixed valence implicates the involvement of charge sector, but also there's some clever thermodynamic measurements which indicate that the spin, something like local moments, can still be defined. And in many ways, it seems to connect with another famous quantum critical heavy fermion system, the ytterbium aluminum boron 4, that's also mixed valent. So we studied, so we expect that in this particle asymmetric case, the charge, the scale over which that the charge response, if it's singular, the scale over which it is singular would be detached from the scale over which the spin response is singular. And we did the real frequency response calculation using the numerical RG method, and indeed showed that the charge sector obeys omega t scaling, but this peel off upper cutoff scale is somewhat different from the analogous scales that shows up in the corresponding calculations in the spin sector. So I think we haven't done the lattice model calculation in this particle asymmetric regime. And
what is the difference between the symmetric and antisymmetric cases? What is this one?
So in the particle symmetric case, you take the, say, starting from the Anderson, either lattice or impurity model, and essentially the filling of the F electron is 1. So it acts as a spin. You can map the problem to a spin-spin interaction between the F electrons.
You don't have a hard constraint.
If the on-site interaction is large enough, and if only two of the 4 levels are relevant, that's a particle hole symmetric problem for the local degrees freedom. But here, in essence, you have 3 levels which are important, right?
And so what is the degree of asymmetry? How does that influence the response?
We actually haven't looked at the scaling function. The scaling function should capture that. But the thing we focus on is the following. And this also was partly motivated by the experiments in these systems. If I have the charge degree singularity, such as shown in these calculations, the scale below which, the energy scale below which these singular charge responses is essentially the same as you would get if you calculate the responses in the spin channel and ask what's the energy range of which it's because ultimately the singularity that happens in the charge channel is tied up with what's happening to the local moment physics. But in the particle hole asymmetric case, you could imagine that the 2 sectors are decoupled in the energy range of which, and we do find that.
And for all of these calculations, you're putting in what kind of spin spectrum feedback are you putting in?
So
I know you covered that yesterday, sorry.
yeah, no, but this actually this particle Hall asymmetric case, it's purely both Fermi and Anderson model. It's a single impurity model.
Oh, I see.
So we haven't done the lattice calculation. I described on Monday the lattice calculations in the local moment limits. But I think it will be very interesting. There are these materials which are providing a setting to study this issue. So so I want to go from here to superconductivity, and so far I've described all the besides the impurity models, the lattice calculations are done at the level of the EDMFT, which I described on Monday. You select a single site and embed that into some fermionic and bosonic bath whose spectrum are self-consistently determined. Now, for unconventional superconductivity, that's not adequate because you can only have S-wave on-site S-wave pairing, and that is not favored, given that there's a very strong on-site Coulomb repulsion. So the minimal thing that we need to do, one way to approach, is to formulate the cluster version of this of these equations, and we've done that, and I'll present the results, which are based on the two sites embedded in this fermionic and bosonic bath, and two sites are coupled through the let me just finish this sentence, Pierce, and then there's the anti-ferromagnetic interaction between the spins at different sites, which capture the effective RKKY interactions, in addition to all the terms which are also captured in the calculations that I described on Monday. Yes, Pierce.
Yes, can you put in a form factor that, for example, will build in the difference between extended S wave and D wave pairing?
Yeah, in principle, you can. Right now, we have done the two-site cluster, so the extended S wave and the D wave are actually not differentiated. What's differentiated is the parity even and the parity odd.
But presumably that makes a huge difference in terms of susceptibility to on-site Coulomb interaction. D wave and extended S wave have a very different overlap with the on-site U. Extended S wave will be very heavily suppressed by the on-site U, whereas D wave will not be.
What's the analog of A1G, let's call it a trivial S wave, is extensively disfavored by on-site Coulomb repulsion. So long as I choose pairing, and in this case, it includes both the extended S wave and the D wave projected to the two-site formulation, the on-site pairing amplitude is zero in this formulation, and therefore the on-site Coulomb repulsion, as far as minimizing the on-site Coulomb repulsion is concerned, these two pairing states are the same. Now, there could be shape up.
We have lots of heavy fermion systems with D wave and none of the extended S.
We don't know. We don't know there are no extended S waves.
But extended S has the same symmetry as S, and therefore any optic of charge between the two sites will overlap with the on-site U.
So Pierce, once again, the on-site pairing amplitude of a regular S wave
just saying it slowly won't help you, Qimiao. The fact is that if it has the same symmetry, then it will overlap, and there will definitely be an amplitude.
It's extended S wave. I can choose. Maybe we can talk further, but extended S wave, I'm choosing a channel which is orthogonal to the regular S wave that has a huge on-site pairing amplitude. That's precisely the program.
The same symmetry can't be orthogonal.
I have projections. So take a square lattice. I can have a pairing function, which is k independent, or pairing function, which is cosine kx plus cosine ky.
Right, I understand that, but that's not symmetry protected against cosine kx plus cosine ky plus constant.
So listen, if I want to do something like square lattice, if I want to enumerate all the irreducible representation of the point group, I would need 4 sites at a minimal to capture the different irreducible representations. The problem I'm solving, the cluster does not have the C4 symmetry. So as far as symmetry is concerned, they are independent channels. I have a conventional S-wave channel. I have even parity, which I don't differentiate between D and S-wave because I have 2 sides. And I can have odd parity that's orthogonal, right? So as far as this 2-side is concerned, there's no distinction between extended S-wave and D-wave because I don't have the square lattice.
Including a form factor in the subconsistency.
We do. We do. That's maybe I can get to that. Yeah.
So
When it comes back.
cluster D with T would be too costly, or
Yes.
I mean it's a bit problematic, right? That you need to use a projection and you break the symmetry by you use any tricks to restore the symmetry
Of the square lattice.
Yeah.
No, I'm not.
Talked about how you can restore the C4 symmetry.
One can, but at the moment, it's a very first work. It took us many years to get to this point, and I think we've set a stage to do the projections in a realistic point group that's captured by the cluster. I'm not saying that's not an important problem, but I think the zeroth order, even this 2-side, is capturing much of going beyond conventional pairing and has never been done. Any other questions? Comments? So I'm going to set up a few basic things before I get to the pairing, because so what's the physical intuition that one could have the favored even parity spin singlet, either extended S-wave or D-wave, which I cannot tell the difference in a calculation, but I can tell between the conventional and unconventional pairing, or singlet versus triplet with parity even versus parity odd. And so one way to gain intuition is to look at, again, as Subir asked, the self-consistency aspect. Before I study the self-consistent problem, I'm going to just fix the fermionic and the bosonic bath. So it's a well-defined cluster version of the Bose-Fermi-Anderson model that I talked about. And this problem actually is also itself, even in the normal state, there's some rich aspect to it. The physics that this cluster calculation captures that the single-sided calculation does not is that now I have the chance for the bond singlet spin correlations to be captured. And in fact, if you look at the phase diagram of this model, there's a Kondo part. So G is the coupling to the bosonic bath of the Bose-Fermi-Anderson model that I described on Monday. And I is the exchange interaction of the sites within the cluster. And so there's a Kondo part when the bosonic coupling is small. When bosonic coupling is large, I can suppress the Kondo part to what I would call local moment phase, but also it's a regime. It's the intersite singlet regime of the phase diagram. So the point is that I have the spin-spin correlations that's anti-ferromagnetic between the sites within cluster. So even in anywhere in this phase diagram, this term exists in the Hamiltonian, and the singular correlations exist. And in fact, you can make the singular correlation to be so large that it's either a phase or a regime, depending on the model, that the single bond type of singlet actually takes over. But anywhere here, that singular correlation exists. And that's very important for the unconventional pairing, because we can, again, study this problem and ask, what's the pairing susceptibility within the cluster? So essentially, it's like an irreducible form of the pairing susceptibility. Which channels are enhanced, which channels are suppressed? So maybe this is relevant to appears to your question. What I can tell based on this, what I can construct here is a parity even, parity odd, and parity even is a spin singlet correlation. Because of the singlet correlation in the normal state that exists, the singlet correlation pairing susceptibility is enhanced as I approach the quantum critical point. If I just follow a scan like this, even though I'm not passing this intersite, the bound singlet phase, I still feel the effect of the singlet correlation. While, yeah.
So first of all, the axis I is the same as IR.
Yeah, correct. Yeah.
Okay, and LM?
LM is when the coupling to the bosonic bath has suppressed the Kondo singlet formation.
Okay, so that's the
In the single impedance model, one knows what the distinction between the two.
The question is, does I make any difference to the LM phase?
So if I'm doing this scan versus I'm doing that scan, there's a difference. If I'm following, so I'm trying to describe that if I have the antiferromagnetic exchange interactions between the sites within cluster, I build up this spin singlet correlations within the cluster, and that makes a difference between the parity even versus the parity odd pairing channel. So the parity odd pairing channel, the susceptibility is suppressed. Parity even susceptibility is enhanced, and that's due to the fact that I'm following a trajectory where the spin-spin interactions within the cluster is non-zero. So that's one way to picture the pairing instability that I'm going to find. Okay. Any other questions? And this is the calculation done at different temperatures, but pretty much captures this physics. Now, you can also ask the following question. I promise that I'm studying superconductivity that develops out of this particular type of normal state that has singular spin responses, omega t scaling, loss of quasiparticles. In this, going from this EDMFT to this cluster EDMFT, is that still happening? And whether the features that have been seen in the EDMFT, are they robust? And has the exponent been changed, etc.? So we address that question. And so this is where the self-consistency of the bosons and the fermion spectrum comes in. The crucial, what's important for the two types of solutions that we can find that I already described also on Monday is the form of the RKKY densive states, which is essentially this I sub ij, which actually I didn't describe in this talk, but I have a picture somewhere among the slides. The Q dependence of it, and you can formulate densive states of it. And the type 1 model that I will first focus on has a jump at the lower edge. And but I'll make I'll show some results to argue that it's actually not that crucial. So with this type 1 model, we found again in this cluster EDMFT the collapse of this infrared definition of the Kondo scale. So I've flipped from left to right to now. The order is now on the right-hand side and the ferromagnetic order. So the important point that the scale that characterizes the strength of the Kondo singlet in the ground state still goes to 0 at the quantum critical point, and associated with it is the a large Fermi-surface to small Fermi-surface jump. And so this feature, and I'll come back to the scaling as well, but this feature itself that's tied up with the loss of the these well-defined quasi-particles is robust. It's still seen in this normal state that I'm setting up for analyzing the superconducting instability. And so just to put this in, this is a purely numerical calculation. In the EDMFT calculation we had, as I described Monday, one can actually make a link between the calculation with various intuitions about fixed points that one gets from looking at the RG flows of the effective Bose-Fermi Anderson model, which from the beginning there's the Kondo fixed point, there's a coupling to the bosonic bath induced suppression of the Kondo singlet, and the separatrix, which describes the approach to the Kondo-destruction quantum critical point. So in the Bose-Fermi Anderson model, just to refresh the memory for those who were here on Monday, but not everybody was here on Monday. The approach to the separatrix on in this phase diagram is characterized by the weight of the quasi-particle Z that's associated with the strength of the Kondo singlet that goes to 0. And that's also seen by, for instance, I've just taken the finite size spectrum of this calculation that we recently did with Kevin Ingerson and his student. That this spectrum is no longer described by Fermi liquid. Well, if you are here, ultimately the low energy part of the many-body spectrum is described by Fermi liquid. So there's a quasi-particle here, and the quasi-particle is lost. This robustness in the EDMFT was even there in spite of in the CeCu₂ problem on Monday. I described that there are more fixed points that was initially anticipated, and this was a surprise to us. But now there's a better understanding of multiple fixed points. So for this cluster version of the analysis we are doing, it could very well be that the cluster Bose-Fermi Anderson model have fixed point structures which are even richer than this CeCu₂ Bose-Fermi Anderson model. But in fact, there's a lot of different forms of the correlation functions on this axis, but on the separatrix, turns out that all these fixed points have a very universal correlation function that for the Bose-Fermi Anderson model. So we suspect that's also what's happening in the cluster Bose-Fermi Anderson model, because otherwise the self-consistent solution cannot retain the structure of the Bose-Fermi Anderson model. And so this was what I described on Monday, that in the CeCu₂ case, in spite of many fixed points, the self-consistent solution still has the destruction of the quasi-particle weight as the magnetic quantum critical point is approached. So our result for the cluster version retains that robustness. And then we can look at the dynamics in this case. So I'm showing you the result for the Ising anisotropic case of the cluster EDMFT calculation. And we again found that there's a h bar omega over kBT scaling. This is done on the imaginary time, imaginary frequency axis, but one can still see the collapse of it with the exponent, which within the numerical accuracy is comparable to the what was found in the EDMFT calculation. We did the same calculation for the CeCu₂ case, and again, this h bar omega of kBT scaling and the exponent retains the form and the value of the EDMFT calculation that I presented on Monday. And so there, let me just show you the exponent that we calculated for the Ising case in the past, which is somewhere around 0.75 with upper range of 0.78. So this calculation for the cluster EDMFT is within the numerical uncertainty is still consistent with the previously determined value. And this was what I showed for the EDMFT calculation for the SU2 case. And the SU2 case, the exponent of the cluster calculation is essentially set as the EDMFT calculation 0.71 versus 0.72. So that gives lays foundation for us to analyze the superconducting instability. And so what we did was calculating lattice pairing susceptibility and tune the ratio of the RKKY to a Kondo interaction, and see where it becomes divergent. And so these different points represent the divergence of the pairing susceptibility. And so we actually have not studied inside the superconducting phase, but we've identified the instability and reaching the conclusion that this type of quantum critical normal state promotes the pairing stability, and importantly, TC is on the order of some percent of the Baire Kondo scale. And so qualitatively, again, the understanding that in many ways is embodied in this charge channel singular responses and the dynamical scaling, even though the competition is between spin RKKY versus Kondo interaction, is what bridges these quantum critical fluctuations with large spectral wave that destroy the quasiparticles with the superconducting instability. And so I want to connect this back to the scale of TC. So we found in this calculation of a TC that's about 3% of the effective Fermi energy. And I showed you a chart of many heavy fermion superconductors. TC versus the characteristic scale is on a linear line with many other families of correlated superconductivity. And so just to make it individualized case, cerium rhodium indium 5 is one of the demonstrated cases where the Fermi-surface jump from large to small, going from paramagnetic to the order phase, has been explicitly demonstrated by the quantum oscillation measurements. And the T0 scale is somewhere around 40 Kelvin or so, and TC is about just over 2 Kelvin. So it captures the kind of quantum critical fluctuations that I've described. The normal state captures the physics of the large to small Fermi surface change across the quantum critical point, and other scaling properties at the quantum critical point. And our calculation shows that TC measured in terms of effective Fermi energy to be right order of magnitude of this particular case of cerium rhodium indium 5. We can also generalize the calculation to what I call a type 2 models that I also described on Monday, and I'll give a slide show more explicitly what I mean by that. And I made a case on Monday that even the SDW quantum critical point, the order parameter fluctuation description of the quantum critical singularities only happens at very low energies, and that's because the spin density wave order, the temperature order in transition temperature is small compared to the Baire Kondo scale, because you have to first form the quasiparticles, and then these quasiparticles develop instability. And so in fact, this calculation shows that at most 5% to 10% of the Baire Kondo scale is the crossover scale, below which you have the order parameter fluctuation description, and above which much of what I said about this type 1 model still applies to this. And we have more concrete demonstrations of scaling, etc. That shows here. And this is a scale which I described on Monday. I don't have the time to repeat the reasoning, but the point is that you can tune from the purely type 1 case to purely type 2 case by designing these this RKKY density state forms, and you can show that this crossover scale is very small compared to the bare Kondo scale, and that's really what's coming in this self-consistent solution. And here again, we also found in this cluster EDMFT calculation found the superconducting instability with TC, which is slightly smaller, but on the same order of magnitude. And we believe that slightly smaller is because, in fact, the pair promoting part is actually associated with the finite energy scales over which these kind of Fermi-surface fluctuations, lots of quasi-particles are operating, and this part could have more of the pair breaking contributions to the development of superconductivity. I want to give a scale of the problem. So silicon copper to silicon 2, the very first unconventional superconductor ever discovered. There's a lot of data in it. The bare Kondo scale is on the order of 20 Kelvin. And this crossover scale going from regime where, for instance, the spin damping extracted by inelastic neutron scattering being linear in temperature to the regime where it's T to the 3½ or from some specific heat versus temperature features is estimated to be about 1 Kelvin based on data of Oliver Stockert and from Dresden. And so that indeed has this characteristics that the crossover from the regime where it's the dynamics quantum criticality is controlled by the order parameter fluctuations to the regime where it goes to this more unusual form with large spectral weight is happening at a temperature 1 Kelvin. That's much smaller than the bare Kondo scale. So we want to connect this kind of calculation with the overall features of superconductivity in systems like silicon copper to silicon 2. So let me. How much time do I still have?
Well, we are. We've got half an hour of discussion for that.
So maybe I take a few minutes just to wrap it up, and I can continue.
The end time is 11:20.
Okay. Yeah, I'm almost there. Yeah. So I want to, because of the topical interest of ytterbium rhodium 2, silicon 2, the extreme low temperature superconductivity, I want to present some effort we have made in that connection. So ytterbium rhodium 2 silicon 2 is probably the most exemplary form of heavy fermion, quantum critical heavy fermions with the Fermi-surface jump as extracted by the Hall measurement that I talked about on Monday, by the omega over T scaling in the charge channel, as I mentioned, and so on and so forth. Superconductivity has been a long slog, and it's still a developing story, and the heroic efforts of going to millikelvin range and see whether the superconductivity is a continuing, and I think it's a mind-boggling line of experimental effort. Given the nature of the normal state that ytterbium rhodium 2 silicon 2, I would say undoubtedly exhibit as distinct from the spin density wave type of quantum critical point in any temperature range that has been measured. So we decided, we haven't done the lattice calculation, just ask the question, giving the recent indication for possible triplet pairing, and I'll describe what the experimental, what's the basis of that statement experimentally. We've done the calculation of, again, just cluster, Bose-Fermi-Anderson model without self-consistency, and at the level that I was describing the cluster, and there's a spin singlet correlations induced by the antiferromagnetic RKKY interaction, and the consequence of that for the susceptibilities of pairing in the different channels. So the CeCu₂ case I already present to you, spin singlet is favored. All three channels of spin triplet are disfavored. As lambda is a tuning that I said maybe 20 minutes ago, that reaches in the cluster-Bose Fermi-Anderson model, reaches from the Kondo side to the Kondo-destroy side. And somewhere here is the quantum critical point. Now, we did the same calculation, but allowing the exchange interaction to be anisotropic. And so this is a typical case. The spin flip interaction is, say, just 20% of the longitudinal interaction. The ratio doesn't matter that much, doesn't affect the result drastically. And so with the Ising anisotropy, I have to differentiate the three channels of triplet pairing. One plus one minus one are the transverse ones, and the orange one is the SZ=0 channel of the triplet pairing and the susceptibility associated with that. So the important point is that this and the blue one here is the spin singlet channel. So you can see that with enough Ising anisotropy, the spin singlet channel, the pairing in the spin singlet channel, and the pairing in the SZ=0 component of the triplet channel, they are nearly degenerate. And this, on top of that, the fact that, so let me show you the data. The fact that the quantum critical point is actually reached by a magnetic field, and the magnetic field will be more hostile to the spin singlet pairing than to the spin triplet pairing, gives the possibility, maybe even likelihood, that if superconductivity does develop near the critical field, which for the in-plane orientation is about 60 Tesla, 60 millitesla, the triplet channel would be favored as far as superconductivity is concerned. So I was involved in the work for looking for superconductivity at the extreme low field limit, the experiment of Irving Schubert, Frank Staglish, and we got more than what we bargained for. It was great. Superconducting features were observed at around 2 millikelvin or so. Some precursor things here, but there's a giant specific heat gamma of 3 orders of magnitude larger than what we even familiar with in the heavy electron systems, and so that clearly is a nuclear spin. So we had some kind of lambda analysis which says that the nuclear spin would through some secondary electronic or degrees freedom, magnetic degrees freedoms would reduce the primarily electronic order and push the system closer to quantum criticality, and that favors the development of superconductivity. The Vienna group has now done the resistivity measurements, and there's superconductivity in low field, but the fairly remarkable conclusion is that the superconductivity may be even persisting at the critical field of 60 millitesla, in-plane field 60 millitesla, and moreover, they did the nuclear enriched variant of this material to find indications of this being decomposed into 2 domes. Yeah.
Would like to have discussion.
Pierce, thank you for reminding. Let me just really wrap it up. I think this is a very topical. In some sense, I'm presenting it as a discussion, but let me wrap it up. Yeah.
I'd like to have a good ratio of discussion to
I apologize, Pierce. Yeah, let me wrap it up. But I think it's a fairly exciting the fact that at TC of some millikelvin can possibly survive a critical field of 60 millitesla. And this fact and other features led the experimentalists to suggest that maybe there are two domes. This is singlet, this is a triplet pairing. And we want advanced, this is only cluster Bosch-Fermi-Anderson calculus. So in many ways, it's an indication, but we want to put forward this indication as a possible reason for the survival of pairing in the critical field range of ytterbium rhodium to silicon. So this is not probably we shouldn't call it high TC superconductivity, but it's at least seems like highly resilient superconductivity. So I think in light of what Pierce, if I may, just let me take 30 seconds just to flash some connections. So I've said this chart earlier. I just want to make it a point that if you want to go from serum-based F electrons to 5F systems to the 3D based the cuprates, maybe these Fermi-surface jumps and other unusual features of the normal state is a link. And certainly, I mean, these are pretty famous plots. So maybe I don't even need to. I just want to mention that organics and my colleague, just advertisement of the work of my colleague Ming Yi in the FETE-SE systems. The precious ARPAS work is telling us Fermi-surface undergoing drastic changes as you go from FESE side, which is already strongly correlated, to the FETE limit. So I think I've run out of my grace period. Thank you very much.
Okay, we're now all the material there. We're now open for discussion.
Yeah, please.
I was just wondering if you had some sense of how the susceptibilities would trend as you went from SU2 to SUN with increasing N. And I'm not sure if that's experimentally relevant, but it was just.
It's actually a good question. So you can ask from a purely Ising limit to SU2, what is happening? And so the point is that I have more spin flip or transverse channel interactions. And as you can picture, that enhances the singlet correlations, which is why the pairing tendency is enhanced. So I would expect going to SU3, the pairing tendency would be even more enhanced. Now, there could be other things. SU3 models have other correlators that come into play, and maybe they will be detrimental due to additional effects in the normal state that doesn't exist in the SU2 case. But at least there's one aspect of it is that you have further enhanced singlet correlation that should enhance singlet pairing. John had a.
Go back to your phase diagram for Kondo-destruction.
Okay.
So it's in a region where the superconductivity persisted to low temperatures.
Oh, you want a superconducting phase diagram? Yeah. Okay. Good.
So is that the quantum critical point for place where superconductivity persists to low?
Yeah. So the quantum critical point is here at 0 temperature, right? And if you look at the normal state properties, there will be a fan that's covered.
So if you're on the left of that,
yeah,
and you first enter the superconducting phase, what happens when you cross over into the green region labeled AF?
Yeah,
does the superconductivity disappear?
It's extremely. Yeah, it's a very interesting question, and there's a lot of phenomenology, as you know, whether they microscopically, experimentally, whether they microscopically coexist or not. As I said, so far this is the first piece of work. So far we've analyzed the instability coming from high temperature or coming from the paramagnetic side. So what we did was to identify these points. It will be a more involved calculation for the superconducting phase itself. And it will be even further involved if you go into the potentially coexistence region. So I don't have a clear-cut answer, but it's a very important and interesting question. And the people in the field, experimentalists in the field, even can have this intuition of whether they coexist microscopically or they don't. Based on that, they could infer something about the nature of the pairing state, etc. So we certainly have not gone to that point yet.
Yeah, just a brief comment. So it's an experimentalist working on this. I mean, we have evidence of the reactions of the normal state, which is not. So, talk about that.
Yeah, I could certainly imagine that as a possibility. Yeah, P.S.
First, a comment. I don't think that you can use two-side any form of DMFT, whether it's got ionic or not, to properly treat superconductivity, singular superconductivity in the systems. There's a huge difference between extended S and D-wave pairing. This was the classic mistake that the Bell Labs and the Princeton group made in the late 1980s, thinking that ITC could be driven by extended S-wave pairing. And I think that if you only have two sites, you have a method that is completely insensitive to the importance of the phase difference between the X bonds and the Y bonds. And so I just don't see how you can use any type, whichever type of DMFT you're using, to explore the superconductivity unless you properly treat the two directions on equal footing. But having said that, I wanted to ask you, does the method you're using give any insight into the fact that that there's a large Fermi-surface in the phase on the right-hand side? Can you see that in the treatment? Can you recover the F-electron Green's functions? Do you see the large Fermi-surface in the method you're using? And I suppose the question will depend on whether you're doing a Kondo or an Anderson model. But for example, in this calculation here, this is with an Anderson or a Kondo model.
So I mean, we'll work backwards. So the calculation is done with the Anderson model, so I mean, what we can say is whether. So I think I had some. So let me first now address the Fermi-surface issue. We can track the. I had a slide on this point.
What's the various phase shifts, self-energies that come out?
So we can track the singlet, the Kondo singlet amplitude as we march along the horizontally going from paramagnetic phase. Correct. Yeah. So we have susceptibility, we have various other quantities, and we can extract this B star out, and we can see that this B star goes to zero as I'm marching from the paramagnetic part of phase down.
In a DMFT approach, everything revolves around the F electrons, not the integrated out. So,
but I have it's an Anderson lattice model, as you well know. The local quantities which are primarily associated with the F electrons can be fed back to the single particle quantities, right?
of course.
Yeah, and so I'm just telling you how we did it. We are looking at local quantities, and we keep track of this B star as a function of the tuning axis.
I mean, it's clear that if you have an extended S symmetry, if you form pairs between two F electrons at neighboring sites, then of course when you hop one of those F electrons from one site to the other, you will now create an amplitude for on-site S-wave pairing. Now, if of course you've got two bonds with opposite phase, those two hopping processes destructively interfere with each other. So you get no on-site pairing. But if they are in phase, then when they hop to that site, you get a huge amount of on-site pairing, and the on-site U then acts to feed back to suppress the divergence.
I think, Pierce, we
I'm
had
very surprised, in
yeah.
fact, in these approaches, whether that you get any done properly, whether you get divergence in the susceptibility.
So we do keep track of the on-site pairing amplitude, but I think this point that you made similarly in the I mean, I recall we had a discussion about this issue even for the Nick-tides context, and so I can calculate the on-site amplitude, pairing amplitude. It vanishes.
Why does it vanish?
It vanishes, and so I think one has to differentiate two ways of
Why
thinking.
does it
Can I just?
No, I'd really like to understand.
Yeah.
There's no symmetry reason for it to vanish.
Let me. So, if you only keep track of the pairing amplitude on the Fermi surface, then it will not vanish. If just do spin fluctuation calculation, etc., for the when the pairing amplitude is only defined on the Fermi surface. But if the pairing amplitude is defined within energy range, that's covered by, in this case, the RKKY interaction, etc., we are going beyond the Fermi surface. And there, in that case, and that's what this kind of approach is certainly committed to, is that you end up with basically the trivial S-wave channel having non-zero on-site amplitude, and extended S-wave or D-wave would have vanishing on-site pairing amplitude. And that's a simple algebra. It's defined on the bonds, because the pairing amplitude defined on the bonds, there's no on-site pairing. But we can follow. We've had this discussion here.
So there's very little information in the supplementary material to enable one to even track this down from the details that are there.
We'll supply you with information. Yeah, but
okay.
Yeah.
So
So
I think the last slide seemed to imply that you can get triplet pairing even with an anti-ferromagnetic couple.
Correct. Yeah.
So what is the physics of that?
What is that?
What is the physics of that?
So there's a very simple. Just think about. Maybe let me get to that slide, because it's actually. And this issue is actually showing up in various contexts. We've started quite a bit of it. So I think maybe even here. So imagine that you are in the complete icing limit when I don't have a spin flip part of interaction.
Okay.
Then what you would call singular, and as z equals 0 component of triplet pairing, they are completely degenerate, as you can imagine.
Yeah. Okay.
And so in spite of anti-ferromagnetic nature
Yeah.
of interaction. So here I've put some, not that small, some, it doesn't really matter. I put 20% of the spin flip anti-ferromagnetic, the X and Y, SX, SX, and SY, SY interaction. That anti-ferromagnetic interaction to be something like, it's anisotropic, but it's non-zero, 20%, or so you can put 40%, 10%, doesn't make any difference. And you can see that the singular channel, the blue, I don't know whether you can see it clearly. This should be better. The blue points are slightly higher than the orange points. So the spin flip interaction has made the singular pairing channel to be a little bit more favored than triplet, but the triplet is still very competitive. And then on top of that, if I added the magnetic field effect, I can kill the barriers between the two.
Magnetic field, I see.
Because the regime of interest for this particular discussion is, in fact, this part of the phase diagram where the quantum critical point is
So you're saying that spatially uniform
magnetic field.
Well, I mean, the more vortex side is there, but
There's a lot of things that magnetic field comes in several forms. One is the Zeeman effect, and I'm only talking about Zeeman effect.
Right.
There's also orbital effect, which, so you already at the Zeeman coupling level of the magnetic field, you can write down the Landau couplings to see that the triple channel will be enhanced relative to the single channel. So even though in this calculation, this triple channel is still slightly less favored, but still competitive enough that if I subject the system to some Zeeman coupling.
But if I were to measure the dynamic spin stability, it would still be active around the
Correct. And there are some other settings, like my colleague Penjinda has measured the spin susceptibility in uranium ditellurides. And in spite of all the initial suspicions, the absolute maximum of spin susceptibility is actually antiferromagnetic.
Following Sylvia's
Yeah.
question, because it's a triplet, you have odd parity.
Right.
So why do you degenerate? I mean, it's not very clear to me why even at odd parity.
So it's just it's actually, just think about one bond where I have SZ interaction, right? And if you construct, let's see, what's the easiest way? Basically, if I don't have spin flip terms, any cross terms of, so you write down the triplet with C1, yeah, it was a plus and minus sign in the difference. That plus and minus sign would only make a difference if the cross terms are non-zero.
No, I mean, if you have an odd parity, yeah, so I can get to this equals 0.
Yeah.
With D vector, say either X or Y, which is up, up, press down, down, with I imaginary, or you can have up or minus down, down. But you still have odd parity, meaning that if I have a two bonds, I have to change the sign between the two, plus and minus.
Yes.
And I don't know how that can be degenerate with the plus plus.
So in some sense, the orbital part are tied up with the spin. If I have, maybe we can work that out on some paper. Yeah.
Get around it.
Yeah.
If you have a single band, is that Fermi-surface CNF now mix, and there's a C band and F band both nearby the Fermi levels, then there's a way to get around. I don't know how we can do that.
So for me, the argument is just the cross terms that would differentiate between the two vanishes if I don't have any transverse antiferromagnetic spin interaction, but maybe there's some extra factors. So I would like to follow up on what's in your mind.
Just got a sort of stupid technical question for an experimentalist. Can you give me an idea of quasiparticles that destroy some intuitive picture of the objects that are?
Yeah, it's a great question. So the level of understanding is the following. I emphasized that in this cluster calculation, the fact that there's a spin singlet correlations in a normal state, which is promoted by this antiferromagnetic RKKY interaction, but you have to recognize that this is antiferromagnetic spin-spin interaction, right? So in the Kondo lattice limit, it's purely due to spins. So the singular correlation that exists that I see in this phase diagram is promoting the singular pairing. And so the picture really is that I have the exchanging interactions between the spins. It drives this bond singlet pairing correlations. Now the static Kondo amplitude is 0, so there's no quasi-particle. But this charge channel singularity that connects the spin degree freedom with the conduction electron degree freedom, that plays a very important role. That allows that singlet pairing channel to be really transferred to be a charge physical pairing a correlation of the electrons. Without this charge channel singularity at a critical point, I would have a hard time to establish a pairing, the physical electron pairing correlations. I don't know, does that give you some picture? Because you see it in transport, etc. The Kondo effects in your face, and that connects a charge degrees freedom with what's happening in the spin sector.
Great 2 lectures.
Don't thanks me yet. Thank you, Pierce.
We will meet in 20 minutes.
Yeah, thank you.
It's just downstairs. We don't have
Hello. I will keep that on for now. What is the hotkey? That's what I was searching for. Oh yeah, here we go. Yeah. Oh, that's what the hell is that? Okay, well, I will keep it on for now. And I'm sharing already, right? Okay. Well, it seems to have disappeared anyway, so it's okay. It's not working?
No.
Well, I will just.
As you say,
No, I didn't understand, from after listening to emails. It seems like the 20 minutes is discussion, not so much blackboard.
It can be Blackboard if you want it to.
yeah.
We'll figure out the lights.
Yeah, well, I think, there's interludes in my talk which are more pedagogical than others.
Oh, I see.
Yeah, that's kind of,
Because you can't use this thing, but the problem is that if you use this thing,
yeah,
you can't present your slides at the same time.
yeah, that's it. Did I read
But it's a simple switch on here.
okay. Let's not worry about it.
This looks like it's just.
I couldn't find
No,
the.
it's got lights, it's got everything else as
Oh,
well.
okay.
If you work
It's
out
got
that
the-
way.
Oh, yeah.
If I would have brought the way I teach my classes last year with my iPad, and then I can
Me
just write
too,
on
yeah,
the
Yeah.
iPad.
yeah. I have a tablet that connects to the.
Yeah, I should have brought
Okay,
my
can't
tablet
find
in my hotel room.
Scared of touching something.
Yeah.
Nothing working.
No, it's working
okay,
just now.
okay.
I have
I figured it out yesterday.
I just have to-
Because I thought you might not, yeah. carry
Oh, so the
much
tablet
stuff.
would work completely. Yeah, so I'll bring my tablet. Oh, I don't know if there's time today. Not really.
I have an iPad if you want to borrow it.
Oh, this will be too complicated at this
Well,
point.
you just plug it in. Same way.
But I have to.
It depends how you use
I
it.
have to send you my Keynote file and all of that, right? Yeah. Keynote.
Possibly if you're doing it that way.
Yeah, yeah. Oh, you mean this for the?
Yeah, just
questions?
for that bit, for the writing.
The writing bit.
I mean, it depends how you do it, but I tend to plug it into a Mac and then just screen share on the Mac, but have
Yeah.
a window on the Mac, which is
I
mirroring
see.
the iPad.
In that case, then you don't need to transfer the talk into.
Yeah, then
your-
you don't need to do anything.
Right,
But it depends if you've ever done that before. If you've not done it like that, it gets more
Oh.
confusing than necessary.
Sorry, you just connect to Zoom on the iPad separately?
No,
So-
I don't connect at all on the iPad. I plug
Oh.
it into the Mac.
Oh, I see.
You
And
use the
open a
lights
window.
on the
You use
same-
Open QuickTime on the Mac, which then mirrors the iPad. And then
Gosh.
just use that window to do whatever I want to share.
That's the way that a lot of us.
You put
Yeah.
QuickTime on the Mac.
Yeah,
Oh, you just take a.
because
QuickTime.
QuickTime, you say record a
Yeah.
video, but the input is the iPad, not the
Ah.
camera. And then you've got a window on the Mac which just mirrors the iPad, so you can then share that as you like. And the iPad is completely separate, and therefore you don't have to worry about doing anything. And you can do anything you want on the iPad.
All right,
That's worked for
I've
me for
never done
teaching.
that before. I think, all right, I think I
It's-
have pretty
it's
much
up to you.
everything on
Yeah,
the slide.
if it works like this. then
Yeah, I mean, I think my next lecture, let's see, yeah.
Yeah.
If there's something I really need to write to today, I will postpone it to Friday's lecture. I certainly have
Okay.
enough without,
Okay, okay.
yeah, maybe that's just right.
There are options here at the bottom that's like off, low, medium, full.
Yeah,
Like, what are
I tried
those?
it, but I
Yeah.
think that's just the house.
It's the
how-
projector.
Projector, yeah.
Yeah.
Let's try it again, see what,
I don't want to.
No, I don't want to touch it while it's working.
does it change anything? No.
I turned the light off.
Ah, it
Ah,
turns the
so, yeah,
light
it is
off,
off.
so it is. So if I turn, No, those lights are just not working. So we
Because
are,
these aren't working, whereas what you want is that one off and these ones off.
yeah,
I think the lights might
Never
just
mind.
actually be broken.
yeah, the
there
light
is that.
themselves are broken. If I do medium, what does it change?
Didn't change
anything?
anything. No.
But if I do this, then everything goes down. Yes.
Which is
That's
Okay,
that's
so
not-
that
probably not what
no.
in full.
Everything, these lights are just broken.
yeah, so
Yeah.
those lights are just broken. We figured out that you can change the light in the rest of the room. That's great. But yeah, we could turn up the what's the curtains.
Yeah.
It's just here.
Yeah.
Let's make it more difficult.
Where's the
to see
curtain?
screen
Yeah,
when they're
that's
all the
right.
way up.
I actually don't have problem seeing the screen when the curtain is up, but some people seem to have. If I sit here, I don't have problem.
Well, when I use the screen, I can just move the curtains up, right?
I think so.
Which is the curtain button.
Not that, actually, you think that is it, but it's actually here also. Now I can't see what. Blinds here, you can see the
Oh, the
blinds.
blinds. Okay,
Yeah.
fair enough.
Press the blinds and then it's either all up or all down.
Okay, great. See.
Yeah, it's a lot better actually. Now you can see. The only problem is that when you write on that, we
Oh, you can
it's
stop.
not-
No, it doesn't stop. Okay, you can just pause it.
it oscillates if you keep pressing up and down.
Okay.
Yeah.
Yeah, all right. Well, I think that will be fine. If I happen to use the phone.
Because I've also seen other people who write directly on the PowerPoint. So one of my colleagues, they leave a blank page on PowerPoint and write onto it.
Right. I mean, I
Using a
guess for
tablet,
with Windows you can do that because if you have this is not a tablet. It doesn't have that ability.
It's a Mac.
It's a Mac.
Yeah. So
For Mac, I use the iPad.
Yeah.
And
iPad will work, but also actually I don't have an iPad, but I use a Wacom tablet.
I see. And that'll work with Keynote or something like that.
Not quite. I use OneNote, Microsoft OneNote. So I
Alright.
flip between OneNote and the Keynote.
Yeah.
It's not ideal. Yeah.
Too much technology. And yeah, I finally figured out something that worked. And but
No,
I
but
don't want
know that
I want to mess with it.
I know that my colleagues with iPad, they do what I think Sam was suggesting. And that writes also on the Keynote or not?
Well,
Okay, I mean, you have your iPad here.
Yeah.
Just a matter of hooking it to
yeah, just plugging it in.
using a USB-C port.
USB, yeah.
Yeah.
You have a
Well,
cable.
it's yeah, general USB.
Well, all right, let's learn something new.
Let's play
Yeah.
play that a little bit. They should be up here.
This then just plugs in
Well, there's one. Yeah.
wherever you want. So
Okay.
yeah.
I'm sharing the full screen. No, I don't have. Oh, then that has to go here.
It's just a USB thing.
You
Okay.
might have to say you trust it or something.
I have to open. Keynote or QuickTime.
Yeah.
There. And then I say file open.
Yeah.
Or open recording.
Yeah.
New recording.
New recording, new movie recording. And then there should be a way to change the camera. So this little box here, iPad.
I think from Sydney, there's a way to directly show the iPad screen, right?
Yeah.
There it is.
And then it, okay, maybe if I do this, it's easiest.
Okay.
And then you can, I mean, if you want to do it, what I tend to do is just use this app.
All right. Thank
Come
you.
on. And then you've got a screen to write whatever you want on.
Okay, so I can.
What about the guide for the blackboard?
It's broken. We
Oh,
figured out it's
yeah.
broken.
So we'll just have to open the window when that happens.
Okay, this is a.
So we try opening the
Yeah,
window
can make it
now?
black if you
Yeah,
prefer.
it works fine.
Yeah.
Let me just check it.
See,
Good.
this is.
Are you going to do that
Dirty.
rather than this?
Yeah.
That's
Let me
what
get
I
credit.
just heard. Yeah, no, I know this. This is not.
Yeah.
I
The
know how to
beauty
use
of
it.
that is that everyone will see it.
Yes, right, right.
Yeah,
This is
sorry, my
wonderful.
daughter was playing with it. It might be on some weird settings.
Okay, no problem.
Probably a cat killed it or something.
Uh,
Yes.
she's 5, but she finds settings I don't know about.
Okay, well, I can still write.
Yeah,
Okay,
that
good.
works. I mean, anytime you want to, you just put this window up.
Let's see. So now I minimize the window.
Yeah.
And go
And
ahead.
you've got that one. Yeah, that works.
Is the recording still on the last one?
Yeah. I already tried it.
All right, so my,
Remember to unmute the voice.
I think I already have. Yeah, I think you can hear me. People online can hear me.
Sorry, that's okay.
Yeah. But then you will have to do the,
I just wanted to check that.
it's still recording.